Bismillahirrahmanirrahim. Assalamu alaikum students. I'm Dr. Ashar Zahir. We were discussing about the linear programming, and we discussed some important steps that how we should be able to resolve the different problems related to linear programming. There were the different steps, like first of all we'll have to formulate our objective function. We'll have to decide, of course, first about our decision variables. Then we'll have to identify the different constraints. Every organization has the constraints. That constraints may be related to the human beings, that may be related to the machinery. So we'll have to identify those constraints and should be able to represent those constraints in the form of equations or in the form of inequalities. And finally, we discussed about the different graphical method, that how we can find out the best combination of the two, for example, the products, in order to maximize the profit in the organizational setting. Up till now, we discussed mostly about one of the objective function, that is the maximization, in which we were more interested in maximization of the profit. But as you know, we sometimes we are also interested in minimization of cost. So today onward, in this lecture or in the forthcoming lecture, we will discuss some problems related to the minimization of the cost, that how we can minimize the cost again within the particular limits of the organization's setting. And finally, again, the same method will be used, that is the graphical method, in order to minimize the cost. Then we'll also discuss that if there are more than two constraints, how we can put those constraints on a graph, and how this graph will help us to find out the optimal points, that is the with respect to corner point method. And finally, how would we able to minimize the cost in this particular case. So let's start discussing about the minimization problem in perspective of that linear programming technique. So our today's lecture is about minimization, and mostly we will discuss about the minimization of cost. Let's discuss about the different steps, or how it is similar to that method of profit maximization. Again, in this minimization problem, we formulated and solved in much the same way as maximization problems. So the method is almost same, the steps are almost same. There is a difference. We will just discuss as we will go through the different steps of solving of the problems. In the graphical approach, an ISO cost line is used. You remember for the maximization of profit, we talked about the ISO profit line. So now if we are interested in the minimization of cost, so we will talk about the ISO cost line, not the ISO profit line. The objective in this particular case is to move the ISO cost line inwards until it reaches the lowest cost corner method, or lowest cost the corner point. So class, as you remember, when we were discussing about that method which may be helpful to find out the optimal point, that is the ISO profit line method, what we did, we put some hypothetical value in the objective function which comes under the area of the feasible region. Then what happened? We try to move that profit line away from that feasible region up to the end point of that feasible region, so that we can find out the optimal point. So the point is, we try to move away that ISO profit line. But if we are interested in the minimization of cost, then what we will do, again we will take some hypothetical value for that cost function, then we will try to move it inward rather than going outward. That was the case with that profit maximization. So that is what is different in case of that ISO cost line and ISO profit line, that is in ISO profit line we move away, and in case of ISO cost line method we move inwards towards the last point of the feasible region, so that we are able to find out that what is the optimal point which would tell us about the optimum combination on x-axis and on y-axis, which can help us to minimize the cost. So that is what is different in case of minimization problems. So let's take an example of that minimization problem. Suppose x1 is the number of tons of black and white picture chemicals produced, and x2 is the number of tons of colors pictures chemicals produced. Our total minimization cost function is equal to 2500 x1 plus 3000 x2. Now what is meant by this particular cost function? It means that if if we produce 1 unit of x1, it will bear the cost of 2500 rupees or $2500. Similarly, if we produce 1 unit of x2, it will bear the cost of $3000. So if we produce x1 number of products, and for that is the black and white picture chemical. So if we produce 1 unit of that black and white picture chemicals, then it will bear a cost equal to 2500. And if we produce 1 unit of that color of picture chemicals produced, then it will bear the cost of 3000. So the total minimization cost by adding the total cost in either these cases will be 2500 x1 plus 3000 x2. In this particular example, this cost function is already given to you. We were just interpreting that what is meant by that cost function. Now again, there are some constraints as were there in the case of profit maximization problems. Here the constraints are, the first constraint is x1 should be greater than or equal to 30 tons of black and white chemicals. So we cannot use the value of x1 less than 30. Its value should always be greater than or equal to 30. So you must remember that when we were starting the linear programming problems, we talked about 3 types of constraints. One constraint was equal to and less than constraints. The others were equal to and greater than constraints. The other constraints may also be in the form of equation, that is equality. So in this particular case, this is the case of equal to greater than constraint. Previously we have just talked about the less than equal to constraints in case of profit maximization. So in this case, this is the example of greater than equal to constraint. The second constraint in this particular case is x2 is greater than equal to 20 tons of color chemical, which means that if we want to produce a product by the combination of both of these chemicals, then this is the limit of using that chemical. If we use below that particular limit, that will not work actually for the chemist or some operation manager. So these are the 2 constraints, that is x1 is greater than or equal to 30. The next one is x2 is greater than or equal to 20 tons of color chemical. There is another constraint, that is x1 plus x2. Again, it is equal to or greater than 60 tons. That is the sum of x1 and x2 quantity of those chemicals should be equal to or greater than 60. So this is the third constraint. So in this particular case, there is a cost function in which we are interested to minimize it. There are 3 constraint functions, and again we have represented these constraint functions in the form of inequalities. x1, x2 is greater than 0. These are the non-negative constraints. Now again, we have already discussed that what are the non-negative constraints. Non-negative constraints are taken in the sense that x1, x2 value should not be and cannot be less than 0. That cannot be negative, because we are talking about the quantity of a product, and the quantity of the product used or particular chemicals used cannot be in the negative. So these are the non-negative constraints, that the value of x1 and x2 is always equal to or greater than 0. So these are, so this is the particular analysis of the problem presented in this particular situation. And now let's solve this situation, and again almost the similar method will be used as we used in maximization problems. Now class, we have first constraint. First of all, we already have the cost function represented in the form of an equation. Now what we'll have to do, we'll have to draw the different constraints on a graph. Now this is the graph, and again this is the x-axis and this is the y-axis, and again with the interval of 10 you have taken the values on x-axis and you have taken the values on y-axis. So first of all we will draw the first constraint. And what is the first constraint? That is x1 is equal to or greater than 30. There is no value of x2 for this particular constraint. Now how we will draw this particular constraint on our line? Now this is the x-axis, and our inequality is x1 is greater than or equal to 30. Now this is the point on x-axis where the value of x1 is equal to 30. Now we will have a point at this particular x-axis, and we will draw a straight line parallel to the y-axis. Now this is actually the line for this particular constraint, which we have converted into the equality. We have already discussed that the first step for the inequalities are that we will have to first convert it into the equality, and then we will convert that equation and we will draw that equation on graph. So this is x1 is equal to 30, and this is the point on x-axis. There is no y-axis, means that we will draw the line parallel to y-axis. As our constraint is x1 greater than or equal to 30, if we consider only this particular line, then our feasible region only for this particular line or this constraint is the area away from this line. Now this one is not the feasible region because it is less than or equal to 30. You know, these values are less than or equal to 30, but our feasible region for this particular constraint is this one. But again, we are also interested in some other constraints. Let's draw the next constraint. What was the next constraint? Our next constraint was that the value of x2 should be greater than or equal to 20. Now x2 is, we have taken that x2 on y-axis, and this is the point where the value of x2 is 20. Again, in this case there is no value given for x1. It means that we will draw a parallel line that is actually parallel to x-axis. So this is this line actually represents our second constraint, which is converted now into the equality, that is x2 is equal to 20. Now again, if we consider the feasible region only for this particular line, that will be the region away from this line. Again, we are talking about the greater than equal to constraints. Either the values will be feasible on this line because of that equality sign, or we'll have to move away from that line, that is greater than sign. So what is the common region up till now? We have just drawn two constraints. There is a third constraint, we'll also draw it, but up till now we have drawn two constraints, and if we only consider these two constraints, then our feasible region will be what? Now this area will be our feasible region. Why this is the feasible region? Because this is the area which is greater than this line as well as greater than this line. So this is our feasible region. Now let's draw the third constraint, that is x1 plus x2 is equal to 60. Now again, for this particular constraint we will use the similar method, that is we'll have to identify the different points on this particular equation, that what are the different points to which we can draw a particular line for this equation. Now how we will get those points? First of all, again the same method, you will put x1 is equal to 0, you will get the value of x2, and then you will put the value of x2 is equal to 0, and you will get the value of x1. So in this particular case, because this is the equation like x1 plus x2 is equal to 60, the points will be 0, 60 and 60, 0. Now this is the point that is representing the point 60, 0, that is the x-axis value is 60 and y-axis value is 0, and this is the point that is 0, 60. X coordinate is 0 and y coordinate is 60. So what we will do, we will just link these 2 points in the form of line, and this is our actually third constraint. Now class, up till now what we did, we draw all of the 3 constraints on the particular graph in order to have the idea that what can be our feasible region. Now what is feasible region in this case? Again, this is the area which is away from all of the 3 lines, that is the line 1, line 2 and line 3. This is our feasible region. Now again, you must understand why this sort of region is the feasible region, because this is the area which is fulfilling all of our limitations, all of our constraints, because in all of these 3 cases we were interested in equal to and greater than sort of condition. So this area will be the feasible region. Now the next point is, we have identified our feasible region. Now we'll have to identify that what is the optimal point on this particular feasible region which can maximize our profit. Now class, again in this particular method we can use the 2 methods as we have already used in case of that profit maximization case. The one method is that ISO cost line in this particular case, which was termed as ISO profit line in that of maximization case. So either we can use that ISO cost line method, and what is the ISO cost line method? That is, we will just take some hypothetical value for our cost function in order to draw the cost function somewhere here on that feasible region, and then what we will do, we will change the those hypothetical values of our cost function to move it parallel towards this particular line, which is the outermost line in this particular case. So we'll move inward in this case. You remember when we were discussing about the maximization problem or the profit maximization problem, we were taking away the line. But in this particular case, if we are interested to use that ISO cost line method, we'll have to move that ISO cost line towards that origin, so that we can find out the extreme point of that feasible region, which is actually, or which may actually your optimal point. But again, we can always use that corner point method, which is sometimes more suitable method used for linear programming. So if we take into account the corner method, we can easily identify that at what points our cost may be minimized. Now again class, this is your feasible region, and what are the corner points? You know, linear programming guides us that our profit may be maximized or cost may be minimized on any of the corner method. So important are the corner method. So this is our first feasible region, and this point and this one is our corner point. So there are 2 corner points in this particular case, that is the point A and the other one is the point B. So our profit will be maximized either at this point A and this point B. So you must understand that how we can identify the corner point in that minimization case. That is almost similar that we used for that profit maximization problem, but in this particular case we are actually interested in the area which is outer side of the particular lines. So in this particular case, the feasible and the most corner points are point A and point B. Now what we'll have to do, we'll have to determine the coordinates for this point A and B. And finally, we will put these coordinates in the cost function so that we can have the different alternatives. And again, that cost function will tell us that what is the optimal point, either A or the point B. Now class, let's suppose we take into account the point A. Now this is our cost function, that is 2500 x1 plus 3000 x2. Now you people must have known that how we calculate the point A. Now you can see that point A is the intersection of this line where y is equal to 20 and the intersection of this line where x1 plus x2 is equal to 60. So what we will do, this is the point where x2, which is actually on the y-axis, this is the point where the value of x2 is equal to 20. So this is the point of intersection. Because there is no x1 involved in this particular case, what we will do, we will put this value of x2 is equal to 20 in this equation. Why will do it? Because this point is the point of intersection of both of these lines. So by putting x2 value equal to 20 in this equation, x1 is plus x2 is equal to 60, we will get the value of x1 equal to 40. Okay? So that is the point which is the point A actually, and if we put that particular point, that is x1 is equal to 40 and x2 is equal to 20 in that cost function, we will get the value of cost function equal to $160,000. So you see what we did, we identify the corner point, which was actually the intersection of two different lines. So we solve those two different lines, as you have already solved different lines in case of that maximization problem. So we get the values of x1 and x2 equal to 40 and 20. Putting that value in the cost function, we got the total cost at one of the corner point equal to $160,000. Now let's consider the other point, the other corner point, that is the point B. Now how we can find out the coordinates for the points B? Again, this is the point B, and as you can see that at the point B is the point of intersection for this particular line that is parallel to y-axis and this particular line, that is x1 plus x2 is equal to 60. As at this point of intersection, the value of x1 is equal to 30. We will put this value of x1 30 in this equation, that is x1 plus x2 is equal to 60. So we will get the value of x2 equal to 30 as well. So the point will be 30, 30, that is x coordinate is equal to 30 and y coordinate is equal to 30. So in this way we can find out the coordinates of the point B. Now if we put this point B on this cost function, that is 2500 x1 plus 3000 x2, putting x1 is equal to 30, x2 is equal to 30, we can get the cost function equal to $165,000. Now class, we identify the most feasible region, then we identified the corner point method, referring to that corner point method of maximization or minimization of cost. And in this particular case, again, we were interested in minimization of cost. We find out the intersection points. We put out the values of the corner points into the cost function. We got the two values of cost functions, and finally we can decide that at what combination of x1 and x2 our cost may be minimized. So what is that combination? That is the 40 units or 40 tons of this one x1 and 20 units or 20 tons of this product x2 will minimize our cost. And what is the minimized cost? That is $160,000. So this is our minimum cost function. By using this sort of product mix for our chemicals, that is x1 and x2, we can minimize our cost. So students, this was the particular example that how we can minimize the cost by using that linear programming method. And again, in this particular case, we use graphical method. Up till now, we have talked about only the graphical method of linear programming, and as we discussed earlier, that there are the two methods which can be used to solve the linear programming related problems. One is the graphical method, the other one is the simplex method, but up till now we have used that graphical method. Before our today's lecture, we were practicing about maximization problems, that how we can maximize our profit. And today in the first example we discussed about the case that if we are interested in minimization of the cost, then how we can find the combination of our product mix so that our cost may be minimized. Let's take another example of that minimization of cost function. Now suppose the cost function is given to you as c is equal to 40x plus 50y. Now this is our cost function in which we are interested to minimize this cost function. So this is our main cost function. There are three particular constraints in this particular case, that is 3x plus 5y is greater than or equal to 150, and we have represented this inequality by that number 1. The second constraint is 5x plus 5y is greater than or equal to 200. The third constraint is 3x plus y is greater than or equal to 60. Now again, all of these three constraints are greater than or equal to. Up till now we have discussed the different cases in which there were either the constraints that were less than or equal to. Now we are discussing about the constraints which are greater than or equal to. There may be the constraints which are the mixture of that less than, equal to, or greater than, equal to, which means that suppose it may be the case that some organization may have some constraints in which for which some of the constraints in we are dealing with less than equal to, and in some of the constraints we may be interested for greater than equal to. In the next coming lecture we'll also discuss one of that type of example. So in this particular case there are three cases and the constraints which are represented by these three inequalities. Again, non-negativity constraints are xy greater than or equal to 0. Again, non-negativity means these variables cannot have some negative value. So this is with relevance to that non-negativity constraints. Now again class, you already know that how to solve these equations. First of all, we will take the equation 1, that is the actually inequality 1, inequality into 0, and by putting x is equal to 0 we can get the value of y, and by putting y is equal to 0 we can get the value of x. So we can have the 2 points for that particular constraint, that is 0, 30 and 50, 0. So now we would be able to draw this these two particular points on the graph in order to have a line for this particular constraint. This is the second line, that is 5x plus 5y is equal to 200. Again, by putting x is equal to 0 we get the y value as 40, and by putting y is equal to 0 we get the value of x 40. So again, these are the 2 points which we will draw on that particular graph in order to represent our constraint number 2. For the third line, again the equation is 3x plus y is equal to 60. That is, we have converted that inequality of constraint into the equation form. Putting x is equal to 0 we get y is equal to 60. Putting y is equal to 0 we get x is equal to 20. Again, we have the 2 points, and which can be used to draw the third line on that particular graph. This is the particular graph in this particular case. Now what we will do, we will just plot those constraints in this graph. Now class, this is our first line. This is our first line which is represented by that number 1. As I told you that whenever you are drawing these sort of graphs, it is always better to give some number when you are drawing that particular line on this graph. So we have given this line the number 1, so that we can easily identify that from where that line is being starting and at what point it is being ended, and at what points a particular line intersects with the other points. So it is always good to draw that graph in that particular fashion. This is our first line, this is our second line where the coordinates are 40, 0 and 0, 40, and this is our third line represented by this number 3, and these are the relevant coordinates on x-axis and y-axis. So we have drawn all of these 3 lines. Now suppose we are interested in to find out the feasible region. Then what will be the feasible region? Because again, in all of these 3 constraints, we are interested to find out the area which is away from all of these 3 lines, because of that greater than equal to sign. Either we will operate on the line or we will operate away from the line. So we'll have to find some common area which is away from all of the 3 lines. So as you can see from that shaded area, that this is the feasible region for this particular example. That is point A, that is point B. We don't know the value of point B yet, but we know that point B is the intersection of line 3 and is the intersection of line 2. So we can always calculate the coordinates of point B. The third feasible point or the corner point is C. Again, what is point C? That is the intersection of line 2 and the intersection of line 1. Again, by solving the line 1 and line 2, we can get always the coordinates of C. And the last feasible point is D, which is actually on the x-axis, for which we are already know about the coordinates, that is x is equal to 50 and y is equal to 0. So class, our corner points are A, B, C and D. These are the 4 corner points which have been identified by using that corner point method. Now our cost will be minimized at any one of these 2 points. But in order to identify the optimal points, we'll have to calculate the coordinates for this particular point B and this particular point C. So let's solve equation 2 and 3 in order to find the coordinates of B, because B is the intersection of line 2 and 3. This is line 2, this is line 3, and again we will multiply equation 3 by 5 in order to equate the coordinates of y-axis. So we will multiply equation 3 by 5 in order to equate the coefficients of y. We will subtract both of these equations and finally we get the value of x equal to 10. Now by putting this value of x equal to 10 in either in the equation 2 or in equation 3, we will get the value of y equal to 30. Now class, we have the coordinates for point B, that is 10 and 30. The next corner point was C, that was actually the intersection of line 1 and line 2. Now again, this is the line 1 equation, this is the line 2 equation. Now already the coefficients are same, so we'll just subtract both of these equations and we will get the value of x is equal to 25. Now again, by putting the value of x is equal to 25 in equation 1 or 2, we get the value of y equal to 15. So this is our next point, that is the point C, 25 and 15. Now what we did, we calculate the coordinates for our points of intersection of the different lines. Now we are in a position to make that cost table, so that we can put the different values of these corner points in the cost function, and that will give the idea that how we can minimize our cost. So this is our cost table. These are the corner points, that is the point A, point B, point C and point D. These are the relevant coordinates for these corner points. Now if we put A, that is x is equal to 0 and y is equal to 60 into this cost function, we will get the value of cost equal to 3000. Next, If we put the value of this b coordinates, that is 10 and 30, into this equation, we will get the value of cost function is equal to 1900. Similarly, for coordinate c, we get the value of cost function equal to 1750, and again for value of d, we will get the cost function is equal to 2000. So these are all the feasible alternatives available for the operation managers, and out of which we'll have to again select some optimum combination. Now, what is actually meant by this combination? Let's talk about the point D. Point D means if we are only producing that product A or X1 and we don't produce for product Y, then the total cost will be equal to 2000. Similarly, what is meant or what is the combination at this particular point C? The point C indicates that if we produce 25 units of first product and 15 units of second product, then the total cost will be equal to 1750. If we compare all of these costs, it is clear that this is our minimum cost, because in this case we are interested in the minimization, not the maximization. So this is our minimum cost, and what is the final decision? We should produce 25 units of X1 and 15 units of X2 in order to have that minimum cost, that is 1750. So this is the example that how we can minimize the cost by using that linear programming method. Okay class, let's take another example. The Queen City Nursery manufactures bags of potting soil from composite and topsoil. So these are the two components of that potting soil, that is the composite and topsoil. Each cubic foot of composite cost 12 cents. Again, while reading this scenario or while reading these problems, what you'll have to do, you'll have to identify the cost function, you'll have to identify the different constraints. That is the purpose of going through that particular situation. Now we have the idea that if each cubic foot of composite costs 12 cents, 12 cents means 0.12. That is the 12th part of that 100. So 0.12 is the cost for single cubic feet of composite. Now what are the constraints? Now this each cubic foot of composite costs 12 cents and contains 4 pounds of sand, 3 pounds of clay and 5 pounds of humus. Now these are actually decision variables. That is, the decision variables are related to that composite and that topsoil. Now each cubic foot of topsoil costs 20 cents. Again, if we produce 1 cubic foot of topsoil, it will cost us 20 cents. So up till now, what is the cost function? We can always identify the cost function. Then that in this particular case, the cost function will be equal to 0.12 x1 if we represent x1 for that composite function, and plus 0.2 x2 if we represent x2 by that for that topsoil function. So this is our cost function actually. Each cubic foot of topsoil costs 20 cents and contains 3 pounds of sand, 6 pounds of clay and 12 pounds of humus. Each bag of potting soil must contain at least 12 pounds of sand. Now what is this? This is the constraint for that particular component, sand. At least 12 pounds of clay. At least means either we should have to equal to this amount or we should have to greater than this amount, but we cannot take less than that amount. So this is the particular case of again equal to, greater than. So these values help us to identify those constraints. Graphically or with the corner points, find the best combination of composite and topsoil. Now composite and topsoil, these are decision variables which may be represented by x1 and x2 or which may be represented by x and y, that meets the stated conditions at the lowest cost per bag and identify the lowest cost possible. So class, what we did, we just analyze this problem, and after analyzing this problem we have the idea of that cost function, we have the idea of different type of constraints which are again related to sand, clay, humus. So we can always draw that inequalities for each of these constraints. Now let's put all the information in the form of a table. Now you can see that this is the case of Queen City Nursery, and we were talking about the three constraints. One constraint is related to sand, the other constraint is related to clay, the third constraint is related to humus, as we have identified by going through that particular situation and problem. This is the cost function, that is 0.12 of composite and 0 plus 0.2 of topsoil. So what will be our cost function? Our cost function will be C is equal to 0.12x plus 0.2y. So this is our cost function. And what will be our constraint functions? Our constraint functions will be, as you can see from this table, and also taking going through the information in that particular situation, we must know that our constraints will be 4x plus 3y is greater than or equal to 12, that is the sand constraint. 3x plus 6y is greater than or equal to 12, that is the clay constraint. Then 5x plus 12y is greater than or equal to 10, that is the humus constraint. And again we have identified these constraints by these numbers 1, 2 and 3. Now up till now what we did, we identify the cost function, we identify the different constraints represented in the form of inequalities. Now again this is the case of cost minimization, that is we are interested to minimize the cost. Now again students, now you have enough practice to solving the different equations. For the equation 1, this is the equation 1, putting the value of x is equal to 0 and putting the value of y is equal to 0 one by one, we can get a point 3 and 0. That is the point on x-axis where x coordinate is 3 and y coordinate is 0. And similarly we can get another point, that is 0, 4, that is the y-axis or the y-intercept. And by connecting these 2 points on the graph, we can have that line equation for this particular constraint, that is the constraint 1. For the second line 2, that is the line equation 3x plus 6y is equal to 12. Again putting x is equal to 0, we get y is equal to 2. Putting y is equal to 0, we get x is equal to 4. So these are the 2 points which may be drawn on the graph in order to represent it in the form of a line. For line 3, that is 5x plus 12y is equal to 10. Putting x is equal to 0, we get y is equal to 0.833. So this is the point which is 0 and 0.833, that is the x coordinate is 0 and y coordinate is 0.833. Similarly we can get the other point, that is the x-intercept or 2, 0. Now again by putting these 2 particular points, we can draw a line on the graph. Now let's discuss about the drawing of these lines on the graph. Now this is a sort of graph. After putting those particular lines on this graph, again you have the x-axis, you have the y-axis. First of all we will draw that line 1 on this particular graph. Now this is the line 1, this is the line 1, which has the y-intercept equal to 0, 4 and x-intercept is equal to 3, 0. So this is the first line equation. Now if we consider only this equation, then what is the area or the feasible area for this particular line 1 away from the line 1? That is the area, all the area away from the line 1 is feasible because of that equal to and greater than 2 condition. But of course this is not the only constraint. We will have to deal with the other constraint as well. In the same fashion we will draw this line 2 on this graph with these coordinates, that is 4, 0 and 0, 2. So this is the line. Again the area away from this particular line is the area feasible for the line 2. Similarly if we draw that particular line 3 on this graph, we can get the line in with the coordinates 0 and 0.833 on y-axis and the coordinates 2 and 0 on x-axis. So this is the line for equation number 3. Again the feasible area for equation 3 is the area away from that line 3. Now again, we are interested to fulfill all the constraints, all the limitations, then we will be able to produce the combination of the different products. So feasible area in this particular case will is that highlighted in this particular graph, and you can see we are now able to identify the different corner points. Our corner points are the point A, whose value we already know, that is the 0, 4. These are the coordinates of corner point A. The other corner point is point B. Now point B, class, is the intersection of line 1 and intersection of line 2. So how can we calculate the coordinates of B? We will solve the equation 1 and equation 2 in order to find the coordinates of B. Another corner point in that feasible area is that point C. So again, C point is the combination or the intersection of line 2 and line 1. So again, we will solve equation 1 and equation 2 in order to find the coordinates of that point C. Now let's solve these equations. Again, this is the equation 1, this is the equation 2. In order to find the coordinates of B, by using simultaneous method, we can get the value of B equal to 2.4 and 0.8. That is, the x coordinate is 2.4 and the y coordinate is 0.8. Okay class, in this similar fashion, we will have to draw a cost table which will help us to identify the different alternatives. Now this is the cost table. We have identified 3 corner points. The value of A and the value of C were already known. The value of B was not known, but we have calculated the coordinates or the values of B by the intersection of that respective lines, and now we will put one by one the value of X, which is actually represented for that composite part of soil, and the value of Y, which actually represent the top soil part of soil. So by putting these values one by one in that cost function, we will get the value of cost function equal to 0.8 at that point A, 0.448 for that particular point B, and equal to 0.48 for that particular point C. Now you are able to identify that what is the optimal combination of those products or parts of X and Y. If you are able to combine or produce that 2.4 kg or whatever is that part of X and 0.8 of Y, then we will be able to minimize our cost, that is 0.448. So this is the minimum cost we can identify within the given limits and within the given constraints. So again class, we have identified and we have discussed and solved a practical problem that how we can minimize our cost in the particular scenario. Let's discuss the last important example of the maximization problem so that we can have the idea that how we can solve the different problems having the different sort of constraints. Now Rinzi Farms grows sugarcane and soybeans on its 500 acres of land. Now class, after reading that particular line, you must have in your mind that this is a sort of constraint, that the total lands are available for this particular case or for this particular farms is 500 acres. Okay? If we represent that sugarcane by X and that soybean by Y, then the one of the constraint will be X plus Y is equal to 500 acres. Now this is our first constraint. Now please go on through the example. An acre of soybean brings $1,000 contribution to the overhead and profit. An acre of sugarcane has a contribution of $2,000. Now again, this information tells us about the objective function, that if you are able to produce an acre of soybean, it will give you a profit of $1,000, and if you are able to produce 1 acre of sugarcane, we are able to produce $2,000. Okay, if you represent the ideal quantity of soybean and sugarcane by XY or x1, x2, then our profit function will be what? It will be 1000 x1 plus 2000 x2. So this is our profit function, that is 1000 x1 plus 1000 x2. Because of a government program, no more than 200 acres may be planted in soybeans, and we cannot plant more than 200 acres for soybean. So that is the restriction imposed by government. During the planting season, 1200 hours of planting time will be available. So the total time available for planting is 1200. So that gives you the idea about another constraint. Each acre of soybean requires 2 hours, and while each acre of sugarcane requires 5 hours. So class, you can have the idea about the another constraints, that total hours of planting available are 1200 hours, and each acre of soybean requires 2 hours, and each acre of sugarcane requires 5 hours. So another constraint may be 2x plus 5y should be equal to or less than 1200. So this is another constraint. The company seeks maximum contribution, that is the profit, from its planting decision. Now what is being required in this particular case, that is we'll have to decide about the decision variables, and after analyzing this particular situation, again we can always identify the decision variables, the objective function and the constraints. We'll have to plot the constraints, and we'll have to solve it graphically by using that corner point method. We have already discussed many examples relating to this sort of problem, so you people may not have problem in solving that particular example. Now again, we are interested in the different constraints. One constraint is the land constraint, that is total land available, and total land available in this particular case is 500. So either we are growing that soybean or sugarcane, we cannot grow on the land which is more than 500 acre. So one of the constraints related to that acres of land is x1 plus x2 must be less than equal to 500. Now again class, this is our first constraint. The next constraint is related to soybean, and this is what, that we cannot have soybean greater than equal to 200. It should always be less than equal to 200. So this is our second constraint, that the x1 value should be equal to or less than 200. Our third constraint is related to that planting point of view, that is 2x1 plus 5x2 should be equal to or less than 1200. Now class, we have identified the profit function, that is z is equal to 1000 x1 plus 2000 x2. We have identified the constraints, inequalities, which are represented by these numbers 1, 2 and 3, and now we are in a position to solve each of these constraints. Again, we can use the similar method by putting one by one x1 and x2 is equal to 0 in all of the three equations. We can get the 2 points which can help us to be drawn these constraints on that graph. So similarly, we will solve the third constraint by putting x1 is equal to 0 and x2 is equal to 0 in that particular equation, and we can get the point of that 600 and 0. Now this is the graph for this particular situation. Now this is our one of the constraint, while the other constraint is this one, and this is the constraint related to that soybean where x1 should be less than equal to 200. So we have drawn all of these three lines. You remember that we have a constraint that is x1 is equal to or less than 200, as there is no value of x2 in this particular case. So what we will do, we will draw this line parallel to y-axis as we did in the previous example. So we have drawn all of these three constraints in the form of these lines. Now again, in all of the three constraints, we are interested in less than and equal to area. So by drawing all of these three lines, you can easily identify that what is the area which is less than for all of the three lines. So this is the highlighted area which actually represent your feasible area. Again, we can operate at any of the point of this feasible region, but of course we'll have to find out that point which will maximize our profit. Again, we can use that corner point method. And what is the corner point method? We'll have to identify the different corners, and we can have the different alternatives for these corners, and then we will be able to identify that what is the optimal corner point. And we have already discussed that the profit will only be maximum at any one of the corner points. So in this case, our feasible region is 0, A, B, C. This is the highlighted area. Now again, points 0 is the origin point where of course the value of x1 and x2 is equal to 0, and we are not interested actually in that particular point. The next point is A, whose coordinates we already know. That is the either case, that is the value of x2 is 0 and x1 is equal to 240 in this particular case. Now this is the value for B, that is the B coordinate, but we don't know about the coordinates of B, but we can always calculate the coordinates of B because it is the intersection of this constraint, and which is represented by a line parallel to the y-axis, and this constraint. So we can always solve these two equations and equations of lines in order to find the coordinates of B. And the third corner point is C, that is 200 and 0. So let's solve these equations. Let's solve it for coordinate B. So coordinate B is the point of intersection of the constraint 2 and constraint 3, and our second constraint was x1 equal to 200, that is x1 equal to less than 200, about the that is the constraint about soybean. So we will put x1 is equal to 200 into this equation, that is the third equation, and we can get the value of x2 is equal to 160. So these are the coordinates for that particular point B. So this point B is the intersection of this equation 2 and equation 3. So again, we are in a position to find out or maximize that the profit function. Now in this particular case, the profit function was z is equal to 1000 x1 plus 2000 x2. Again, class, we have identified the four important points which are actually the corner points. These are the relevant coordinates for each of these corner points, and again what we'll have to do, we'll have to put each of these points into this profit function so that we can have the idea that what are the different feasible alternatives available before the operations managers or any decision making manager. So in this particular case, we'll put x1, x2 equal to 0, and of course the z will be equal to 0, which is not the area of interest for manager. The next point is A, where x1 is where the first coordinate is 0 and the second coordinate is 240, and our relevant profit in this particular case will be equal to 480,000. Again, the third point coordinates are 200 and 160, and see that this is the maximum value of profit, that is 520,000, and these coordinates are giving you the idea that what should be the best combination of the two different products so that we can maximize our profit. And what is the maximum profit? That is the 520,000. So class, this is the example we just discussed in order to better understand the linear programming problems, and most importantly that maximization of the problem, which we have already discussed in the previous lecture, and also we discussed some important examples either for the maximization of the profit or the minimization of the cost. So after doing so much practice for these questions, I think you must be well aware of that graphical method of linear programming, that how we can identify our profit function, how we can formulate and how we can convert the different limitations or the constraints in the form of equations and inequalities, and then finally how we can draw a graph in order to put those constraints on that graph in the form of different lines, and how we can find out the different points of intersection for these lines on a particular graph, and finally how we can draw a table which tells us about the different alternatives, about the different combinations, so that we may be able to either maximize our profit or minimize our cost. So class, these were some of the examples we discussed in our today's lecture and some of the previous lectures, and now I would suggest you all that you must have find out the similar problems from your textbooks. I have recommended already 2 of the textbooks to you, that is one written by the Heizer and his co-authors, and the other one is written by Taha. Both are very good books. So you must have extracted the similar examples, that is the examples of relating to maximization of profit or minimization of cost. And of course you have learned up till now only the graphical method, and we have not touched the simplex method yet. So after doing a lot of practice about that graphical method, inshallah we will move that more comprehensive method of that linear programming problems, that is the simplex method. But I would like and I would expect from all of you that you must take the similar examples, you must solve these examples so that you can find out that how to draw the graphs and how to find out the feasible region and how we can find out the optimal points through that corner point method, and finally how we can maximize or minimize our cost, again which are the most important and prime functions of operations management. And again I would also like to recall our definition of management, that is management is science, and what we discussed in that proper definition, that we are always interested to take the decisions on some calculations, on some mathematical or statistical techniques, on some logical conclusion, or on some sound facts and figures. So that is the best example in order to understand that concept, that is the linear programming, that now you are well aware of this technique of linear programming, that how this technique can help us, of course under the different assumptions in the real scenario, but it of course helps us to find out the different optimal solutions so that we can achieve our prime functions of that profit maximization or cost minimization. Okay class, this is the end of our lecture, and I hope you will work at your homes to practice about all of these related problems, and wish you good luck and thank you. Khuda Hafiz.